Okay, this is the lecture video for MAC 1114 trigonometry. We're in section 9.3 where we're going to discuss the polar form of complex numbers. If you recall from your algebra classes, a complex number comes in this form where it has a real portion and an imaginary portion. Those kind of numbers can be graphed on a grid. And the x-axis now takes the role of the real axis. So when you're going to plot a complex number, to go and graph this real portion, you move out that many units on the x-axis. That's where you move to plot your real portion. And then to plot the imaginary portion, that is vertical movement. You move either up or down. So if you had a complex number like this, 3 plus 2i, you would move out 3 for positive 3 on the x-axis, and then you would move up vertically 2 units to represent 2i, plot a point, draw a ray from the origin out to the point, and that ray represents the complex number. Well, what we're going to be doing in this section is taking these complex numbers and putting them in polar form. In other words, learning how to get an R value out of this as well as a theta value, and we'll put this number in what we either call polar form, but it can also be called trigonometric form. So I was just reminding you of the algebra that you've learned to kind of tie it into things that you've learned before. Here, this is just a picture called the parallelogram method that is sometimes used when we want to find the sum of two complex numbers. Of course, the easiest way to find the sum of two complex numbers is to just, like here you see 1 plus 3i and 4 plus i. The easiest way algebraically is to just add the real portions, add the imaginary portions, which is very quickly you could see it's 5 when you add 1 plus 4, and when you add those imaginary portions it's 4i. But there's also a way to draw it, and we use this in the next section when we're dealing with vectors, though just thought I would throw it in here to just kind of give you a glimpse at it. But if you did want to draw the sum of these two the sum of these two complex numbers graphically, you would use what's called the parallelogram method, and that's also used when we're summing together vectors. And all that entails is, as I was stating up here, the way that you plot a complex number is you move out on the x-axis for the real portion and either up or down on the y-axis or vertically to do the imaginary portion, and that's what I did here. To represent 4 plus I, you would move out 4, up 1 for the 1i, plot a point, draw a ray. To represent 1 plus 3i, you would move out 1 for the real portion and up 3 for the 3i portion. You would plot a point and draw a ray. So you'd have these two rays. So if you wanted to graphically draw this sum, what you would do is construct a parallelogram. You would draw a side that's parallel to this ray, and that would be that side. Then you draw a side parallel to this ray, which would be this side. You would then have a four-sided parallelogram, and the ray that goes from the origin out to the opposite vertex, well, that point right there is 5 positive 5 positive 4i. See, if you were to go out 5 and up 4, you're at this at the sum. So it's just a way to graphically represent the sum of two complex numbers, the parallelogram method. Okay, as stated, most of this section will have to do with you converting complex numbers into polar form, and then learning various operations you can perform on polar form, like finding a product, finding quotients. That's another thing that we can do once they're in polar form. So let's just start with the usual definitions that they start you with in each section, and this just comes from the discussion we've had thus far. In the complex plane, this is called a complex plane because you have a real axis and an imaginary axis. The x-axis is referred to as the real axis. You plot your real numbers along the x-axis, and the y-axis is referred to as the imaginary axis. but just so you know how to plot a plus bi. Okay, this is just a representation, again, of a complex number. If you were going to plot the complex number x plus yi, you have a real portion and an imaginary portion, so you would move out x units for the real portion, up y units for the yi imaginary portion. You would plot a point and draw a ray to that point. But what that forms is a right triangle. And therefore, everything to do with a right triangle applies to these complex numbers. In other words, if you needed to find r, which leads us into this definition, it's nothing more than the Pythagorean theorem. On this picture, you can see that r squared would be equal to x squared plus y squared by way of the Pythagorean theorem. So you can write it like that. You can write r squared is equal to x squared plus y squared. And if you wanted just r, you would take the square root of this r squared, leaving you with just r. So this is equivalent to this. And then you would take the square root of this side as well. That's if you just wanted r, which you're going to want in many of the problems in this section. These other formulas are from section 9.1. This was given that x is r times cosine of theta, y is equal to r sine of theta, and tangent of theta is equal to y over x. But they were initially introduced in section 6.2. And then we just kept using them in different ways in each section. So we will be using those again. Okay, now we come to what's called the polar form or the trigonometric form. It goes by either name of a complex number. When you're putting something in trigonometric form or polar form, you're going to find the r value, and that will be the coefficient of your polar form complex number, and then you're going to find theta. So how are you going to find r? Again, from the formulas right on the previous page. You can find r like this, which again comes from the Pythagorean theorem, and we saw a picture of that on the previous page. And if you want to find theta, you can just use tan of theta is equal to y over x and eventually find theta. Once you find the r and the theta, you're ready to put it in your complex number in trig form. Note that just like when you are presenting a complex number in rectangular form, you have a real portion and an imaginary portion. Your imaginary portion will always be multiplied by sine of theta. So you have to memorize this formula. This is the real portion of the complex number. This is the imaginary portion. Imaginary portion will always be involved with the sine of theta, whereas the cosine of theta will not have an I next to it. Okay, these are just different notations of a trigonometric form complex number. I'm making a notation for you here that this cosine of theta plus I times sine of theta can sometimes be written in a shorthand form, which is called the Cis form, and it's just a combination of sine and cosine. So you would write it with cis. If you see it as CIS theta, that means that the theta belonging to cosine as well as sine is what you're seeing right here. So you will sometimes see a shorthand version for cosine of theta plus I times sine of theta. And if you wanted to write the full polar form complex number in this shorthand form, you would mention the r, that would be out here as the coefficient, just like it's in the coefficient when it's in its full-blown form. And then you would just multiply it by cis, which is just a combination of these, just written as one term. Okay, in this section, I know R has been called the hypotenuse, but here we call it the modulus, or the absolute value of the complex number. In other words, it is the distance from the pole, or the origin, as you may want to call it, from the origin out to the point that was plotted to represent the complex number. Okay, you have been calling it the hypotenuse, the R value. Now it just takes on a new name. And here it's called either the modulus or the absolute value. Theta, we have always called it the argument, and it is called the argument here, the theta that you find by using tan theta is equal to y over x. These answers can also be given in exponential form. When you are going to give it in exponential form, again, you need nothing more than the r and the theta. And that r and theta will be put into this formula if you are asked to give your answer in exponential form. It will just be the complex number represented by z is equal to r times e raised to a power of I times theta. And I typically write the theta, the angle first, and then the I off to the side. But you can write the I first also. That's up to you. So this is our second example. Just trying to draw some more definitions out of you in examples 2 and 3, and then the actual problems start with example 4. So in example 2, it just asks, when a complex number z is written in polar form, this is what it looks like, the non-negative number r, that coefficient out there, is called the modulus. And it can also be referred to as the magnitude. It's just another name that we use for the modulus. It is just the length. It is the distance from the origin out to the complex number. Okay, and part 2 of this question, and then it says, and the angle theta between 0 and 2 pi is called the argument of the complex number. So those are two definitions that were on the previous page. Okay, if z is a complex number, then the magnitude of z, the length of that arm, is which of the following? And that would be, they're really just asking you for the r value. So r is equal to square root of x squared plus y squared. And that would be choice B. Okay, again, just to, so you have, just a visual on this. If you were going to plot x plus yi, you would plot your real number out this way. So you would go out x units, and then this would be your imaginary portion. So you would go up a certain number of units this way. So you out this way, out this way. This would be the point. And then you would draw right to there. And so this r value that you're finding is just the length out to this point, which represents the complex number. And in the complex number, you have to see things as what they are equivalent to. This is the same thing as x, and this is the same thing as y. You're out x units, you're up y units. So from here to here is x, from here to here is y. So when you're finding y, again, r is nothing more than Pythagorean theorem. It's just x squared plus y squared. If you started off by thinking of it as the Pythagorean theorem, and then when you're going for just this length right here, that is when you would take the square root. That would give you the r value that I just discussed for this problem. Okay, so same formulas from sections 9.1 and 9.2 and section 6.2. Okay, moving to the actual problems where we get to use those formulas. So here it says plot the complex number on the complex plane and write it in polar form and in exponential form. So to plot this, the real portion gets plotted on the real axis, and then you would be going up 4i units. So this would be 1, 2, 3, 4 right there. That represents 4 plus 4i. So you want to make sure that when you have to find r and theta in order to put this in polar form. And you need r and theta to put it in exponential form. So you want to make sure that that theta is in the same quadrant as this every time you go to do one of these problems. That's why they have you plot it first, so that you have a visual on it. So let's go after r. R is going to be equal to x squared plus y squared, and I know that this is called, that we see the 4 and the 4i as a plus bi. That is equivalent to x and y. Those are the numbers that we're using there. Just these coefficients, don't put the I in there. So this would be equal to 4 squared plus 4 squared. The a and the b value play the role of x and y in this equation. So this would be equal to 16 plus 16, or 16 times 2. You could take the square root of this. It would be 4 when it comes out, and the 2 would stay inside. Okay, we just found the r value. Then you're going to go on to find theta. So it's tan of the reference angle. Of course, the reference angle and the actual theta are always the same when you're in quadrant 1, as we are right now. We always find theta with y over x, which in this case is, the y value is 4, and the x value is 4. Okay, again, this is a. This is b. This is the same. The a value, or a coefficient, is the same thing as x, and the b coefficient is the same thing as y. Okay, so we want to know, what is the angle associated with a tan value of 1? And a lot of you may have that memorized. That angle is 45 degrees. Or in other words, pi over 4, because they're going to want you to give your answers in radian form. And you can see in the instructions right here, which have been taken from your homework system. Type an exact answer, use pi as needed, type any angle measures in radians. Use angle measures greater than or equal to 0 but less than 2 pi. So in other words, in between 0 and 2 pi. So you're going to want to give it in radian form. Okay, once you get those, the r and the theta, just bring it over here to where the answers go. You're going to put your r out front, and remember the form that this comes in when you report your polar number, or what's also called the trigonometric number. It always goes like this: r is the coefficient, then it goes cosine theta, and then your imaginary portion, which is always related to sine of theta, always paired with sine of theta. You want to pick the answer that has them in that order. Cosine first, and then I sine theta, which means it's going to have to be D. R goes out front. That R value was 4, square roots of 2, and then the theta was pi over 4. And note that that pi over 4, if you were to rotate to pi over 4, you are in quad 1, which is where you need to be, because look, your original complex number is in quad 1. So you have to make sure that that angle you find is consistent with where the complex number actually is. When you find that theta, it goes here as well as here. Close the parenthesis. I mean, they'll have another parenthesis there for you. Write the complex number in exponential form. Well, when you're writing it in exponential form, that's just a formula. A formula for writing the answer. And that formula is like this. It's R times E raised up to a power of I times theta. That's what you're plugging into. I mean, don't feed that into the answer blank, just give the final answer. Maybe you can write it down here to remind yourself of what the formula is. So the R value, once again, was 4 square roots of 2, and then it's E, I times theta. And our theta was pi over 4, so I'm going to write it like this. I like to write my angle first, and then my I. You can put the I in front if you want to, but I like to put the value, then the I. Okay, and that completes example 4. Moving to example 5. In example 5, we have 10 minus 10 square roots of 3i. So let's plot this first so we can see what quadrant we're in, so that when we find the theta, that theta matches the quadrant that this is actually in. So if you were out 10, and you can just approximate, we really just need to know what quadrant we're in. So if you were out at 10, you'd be about, let's see, 8, 9, 10, about right there. And then 10 square roots of 3. I mean, you can get an approximation in your calculator if you'd like. So 10 times second function square root of 3, and that would be 17.3. So 9, 10, and 17. This is 17, 17.3. You can type the coordinates in my math lab, but this is where you would be. Whoops. Didn't pay attention to the negative. I'll backtrack on that. So you would be going out to 10, 9, 10, that's right there. And then you'd be going down to 17.3. So that would be about right there. So that is where your point would be. And so that point represents 10 minus 10 square roots of 3. Okay, so see how this is in quadrant 4? So you want to make sure that the theta that you're giving is in quadrant 4, and that it also complies with the instructions in the problem. Like, for instance, looking at the instructions down below, because this goes with example 5, it says, using pi as needed, type any angle measures in radians. Use angle measures greater than or equal to 0 but less than 2 pi. So in between 0 and 2 pi. Okay, so let's do this problem. So we've plotted it. Now we're going to do our R value, which is just this formula right here, x squared plus y squared. And this, our x is this, also the same thing as the a value. And then all of this is the y value, also known as the b value of our complex number. So it's x squared plus y squared. Okay, and now we're going to simplify that. And so right here we get 100, and then for the next term we get, when we square the negative 10, that would be negative 10 times negative 10, 100, and when we square the square root of 3, we get a 3. So underneath this radical we have 100 plus 300. So altogether that is 400. Okay, r is equal to square root of 400, and the square root of 400 is 20. So we have our r value. Then we have to find the tan of theta. We're going to be finding the reference angle first, and then finding the actual theta, making sure that we're in quadrant 4. So our reference angle here, and you can use your calculator to help you out if you'd like. You can go like this, that this is equal to y over x. Our y is that negative 10 square roots of 3, and the x is the 10. The 10's cancel. So this just ends up being like this. So you can get your calculator to help out if you don't want to draw each part of it. You know how to make your calculator find an angle. You just do an inverse of this value. And that's your reference angle. So the reference angle here is, and you might want to, put your mode in degrees because you're going to recognize these angles much more easily if you're in degrees. So that's just a suggestion. And then goes second inverse tan, feed in that value, negative second square root of 3. Close that up. And you get negative 60 degrees. That's what your calculator gives you, but that's also the reference angle if you just take off the negative, because reference angles are always positive. So if you're trying to give this in as an angle between 0 and 2 pi, which is what the instructions say, you're going to use this as the reference angle. That is the same thing as pi over 3 because they are going to want this in radians. But now to give your final theta, you need to get all the way to this ray right here. Rotate all the way to this ray right here, but have a reference angle of pi over 3. Okay, so think about how much this rotation would have been to get all the way from the x-axis to this ray right here that goes out to the complex number. We've done this a lot in chapter 6, 7, and 8. This is the pi location. It is known as 3/3. This is the 2 pi location. It is known as 6/3. So if you were rotating all the way until you got to this arm right here, but you stopped 1/3, which that's the purpose of this reference angle, is to tell you how much you stopped before getting to the next landmark. There's 2 landmarks, 1 pi and 2 pi. So you were on your way to 6/3, but stopped 1/3 before you got there. So this reference angle gives you the final theta, which is 5/3. Okay, so while the reference angle is 1/3 pi, the real theta is 5/3 pi. Okay, and now you can write your answers because you have the theta. You have a theta that's between 0 and 2 pi. And you also have your R value, which is 20. Okay, so now let's take those values and write our polar form number. Okay, so now remember how the formula goes. It's cosine in the front, I times sine in the back. That would be this one right here. R value goes out front as the coefficient. And then you put your theta in here. It goes right next to cosine as well as sine. If you're asked to put it in trigonometric form, well, then you just use this formula right here. I'll just write it over here. It's just R times E raised up to a power on that E of I times theta. So our R value was 20, and it's times E, I times theta. I write my theta first, and then I let the I hang right off the back, put it right off to the side there. Okay, and so that's all we need for example 5. Moving on to example 6. Okay, in example 6, again, we're practicing making sure that our theta is where this complex number is. And again, that's why you're starting every problem plotting the number. Again, the reference angle, like in almost every section, becomes the most important part of the problem because you never get to the point where you get to the real theta unless you understand the role that the reference angle plays. So let's first plot and see what quadrant we're in. If we're out 13 and down 13, again, we're in quadrant 4. So out 13, down 13. going to be right there. Okay, that is where our complex number is. That represents 13 minus 13i. Try and write a little bit better. And we want to get a polar representation for that complex number. So we start off trying to find r with our formula, square root of x squared plus y squared. This is our x, this is our y. Same thing as a and b. Okay, so a value or x value is 13. This formula says square it. Our y value is that negative 13 coefficient, and this formula says to also square that. So you have 13 squared plus 13 squared is 169. This is 169, or in other words, what you have under the square root is 2 times 169. I'm just writing it like that because I know I'm going to turn around and try to take partial square roots. So there is a square root of this, which, I mean, you can already see it in the problem, but so you can see it, it's 13. So square root of that is 13, comes out as a 13, and that number has been dealt with as far as taking square roots, whereas the 2 does not have a square root. So this is your r value, and it is 13 square roots of 2. Okay, then the theta. It is tan of theta. The reference angle first is equal to y over x, and then the y value is negative 13, x value is positive 13, that ends up being negative 1, and regardless of whether it's a 1 or a negative 1, that reference angle is 45 degrees, but you can put it in your calculator if you'd like. You can write, you can just go like this if you want your calculator to figure it out for you, what the reference angle is that's associated with this. You could just go inverse tan of this value is equal to this reference angle. And when you do that, we already have this in degrees. Second, inverse tan, put in that negative 1, close that up and see how it tells you 45 degrees. But if we're talking reference angles, a reference angle has to be positive. This is the same thing as pi over 4. Now take that reference angle and get yourself in quad 4. They want you to spin between 0 and positive 2 pi, not negatively. So they want you spinning that way. And so you're just asking yourself, how far do I have to spin if I'm trying to get all the way to this ray that represents 13 minus 13i, but yet I know that my reference angle, your reference angle is always wedged in between the x-axis and this ray right here. So we know that that is pi over 4. The landmarks, once again, are 1 pi expressed as 4/4 since we're talking fourths here, and this would be 8/4. So if you were on your way from 0 to 8/4, but you stopped 1/4 before you got there, then that answer would be theta is equal to 7/4. And that gets you in quadrant 4 where the actual complex number is. Okay, so we have our actual theta and we have our r value now. And as soon as you have those two things, you are ready to give your polar complex number, or if you want to call it trigonometric complex number. You're ready to give it in polar form as well as exponential form. Okay, just make sure you pick the right one. It has to have cosine in the front, I times sine in the back. That's going to be this choice right here. Your R value is 13 square roots of 2, and then your theta was 7 pi over 4, which goes here as well as here. Okay, moving on. Okay, now we're going to put it in exponential form, and I'll just keep writing this formula so that you memorize it. It's just R times E raised up to a power of I times theta. So that R value is 13 square roots of 2 times E raised up to a power of I times theta. Our theta was 7 pi over 4, and then it has to be multiplied by I to give it in full exponential form. Okay, so that's all the answers that we needed there. Moving to number 7. In number 7, we're at -6 and then positive 7i, so plotting that. That puts us right there. So this represents -6 plus 7i. So we're going to want to make sure that our theta complies with that. Okay, so first we're going to find our R like we always do. R is equal to x squared plus y squared. Okay, so that is -6 squared. This is the x, this is the y, plus 7 squared. So that R value is equal to 36 plus 49, which is square root of 85. 36 plus 49 is square root of 85. Okay, then let's see. Next thing, let's see what they're talking about down here. Read these instructions first. Okay, so now we're going to find the theta. We're doing tan of the reference angle. Which is y over x. This you can't simplify any further. That's why I simplified any further, and that's why I left it like that. Okay, so the y value would be the 7. The x value would be -6. Notice that you're getting numbers here that have nothing to do with special right triangles. If it was a special right triangle where you were going to get a 45 degree or 30 degree or 60 degree, you would be seeing square root of 2 over 2. You'd see a tan value of 1. You'd see tan values of 1 over square root of 3 or square root of 3 over 3, and you don't have that here. So that just means, which is why you're seeing in these instructions, you didn't have this in any of the other problems thus far. It says type any angle measures in radians, rounding to 3 decimal places as needed, because they know that you're getting, something weird here, and therefore you must do it in your calculator. So let's see what 7 divided by 6 is. That just runs on and on, so maybe we won't round it off like that. We can wait to round it off in the next step. Okay, so if we want a reference angle, let's do what we always do. We'll go inverse tan to get an angle of the value that you have right here, -7/6, and that will be equal to our reference angle. Now our calculator may give us a negative value, but we can always take the negative off and use it as the reference angle so that we can then find the real theta. Okay, so let's see what we get here. So we're going to go second inverse tan of -7 divided by 6. Oops, I left it in degrees. Let's change the mode into radians. Change the mode into radians there. Second quit, because you have a radian type number here, a decimal, and you're trying to take the inverse tangent of it. So we're going to go second inverse tan, -7 divided by 6, close that, and you see that you get -0.86217. I'm going to keep that there. But if it's a reference angle, we disregard the negative. So I'm going to keep that many digits. Just hold on to some digits there, at least 5 of them, just for accuracy in the end. And then I'm going to use that reference angle to help me find the real theta, just like I always do. And maybe put a note here that because we wanted the other ones to come out in degree form, so we would recognize them as either being 30, 60, or 45, because we have those pi forms memorized. But here, these are not any of those angles, and you're not going to recognize it anyway. Therefore, you need to have the mode for this particular problem in radians. Okay, so I switched that one to radians. So 86217. Okay, now we're going to make ourselves get in quad 2. Get into quad 2 because that is where your complex number is located. So with this reference angle, we can do this. Okay, whenever you're using the reference angle to get the real theta, you have to ask yourself, how much would I rotate to get right here? Knowing that the reference angle is equal to 0.86217. Okay, you were on your way to 1 pi. You always got to be thinking of these landmarks. Now, I'm not going to bother to rewrite that as a fractional type of pi because the reference angle has nothing to do with fractions. You rewrite your landmarks or whatever the nearest landmark is in fractional form if your reference angle is a radian type measure that's in fractional form, but this is in decimal form, so you want to think of this in decimal form. So if you were on your way to pi, but you stopped this much before you got there, you have to subtract because this theta that you're looking for is something less than pi. And you can't get anything less than pi unless you subtract from pi. So if you want this theta, where this arm is right here, it is equal to 1 pi minus the reference angle, 0.86217, which is equal to, okay, so second function pi minus 0.86217 should give us a pretty good approximation. And it says that we can round this off to 3 decimal places, so 2.279. For that final theta. And we've done that in other sections too. Sometimes we're not working with angles that have to do with special right triangles, but we're working with other types of decimals. So the actual theta was 1 pi minus 0.86217. Okay, so when you go to bring this over here to the final answer, We're just going to look for the one that's in the right form. Cosine in the front, I times sine in the back. That would be this one. Cosine, I times sine. We put our R value out front. I'm going to put here that this was 2.279. And fill this in. So our R value was square root of 85. And then we just put our angles right here. 2.279. 2.279. Close up that parenthesis. Putting in an exponential form, we're always using this formula. Z is equal to, Z just stands for the fact that you're working with complex numbers, but this is the actual formula you're plugging in for exponential form. Okay, so our R value is square root of 85 times E raised up to a power of I times theta. Our theta was 2.279 rounded to 3 decimal places times I. Okay, moving on to example 8. In example 8, it says, write the complex number in rectangular form. So now we're going back the other way. If we're going to try and write this in rectangular form, then we have to think about the formulas that we got from section 9.1 and get our head refocused on the fact that when it's in rectangular form, a complex number, this is a complex number, but it's a complex number in polar form. We've been working to create those in examples, I believe 5 through 7. So we want to go back to this form, complex number that has an A value, which remember is the same thing as X, and a B coefficient on the I term, which is really nothing more than the Y. And then try to remember, how do we get X and Y from R's and Thetas? And so that goes right back to section 9.1, where X is equal to R cosine theta, and Y is equal to R sine of theta. Because if we can find X and Y, that's the same thing as A plus A and B, and we'll be able to write this in rectangular form. This is the rectangular form of a complex number. This is the polar form of a complex number. Okay, so let's get at finding X and Y. So X is equal to, the R value is out front. This is R. When it's in polar form, that's that R value out front. So it would be 4 and then cosine, and then you can see the theta there as well as there, 5 pi over 3. Takes you right back to chapter 6 and all the chapters we've done since chapter 6, where if you want this value, then just rotate to 5 pi over 3. This is 3/3, 4/3, 5/3. 5/3 would be right here, right before you got back to 2 pi. Okay, close up that triangle and think about, if you had rotated to 5/3, then it must be that the reference angle is 1/3, or in other words, 60 degrees. Okay, here's my little picture right here. I'm trying to find the X value because that's really the same thing as A, and I also would like to find the Y value. So remembering the formulas from 9.1, R times cosine theta is going to get me X, and I can plug that right in there. So I drew a little picture. I rotated to 5 pi over 3. left me with a reference angle of 60 degrees, which means this vertical leg is square root of 3 over 2 negative. And then this horizontal leg of the triangle is 1/2. Remember, the horizontal leg represents cosine and the vertical leg represents sine. So when I go to finish this, it's 4. Cosine at 5 pi over 3 is 1/2. 4 times 1/2, 2. So we have our x value, and now we're going to go find our y value. And our y value, as we try to relate the information that we have here, r and theta, to x and y, is r sine theta. So it's r times sine theta. And on this picture that I've drawn, a rotation to 5/3 and the resulting right triangle, the sine theta is this vertical leg, square root of 3 over 2, negative. 4 times negative square root of 3 over 2. Okay, so this is 4 times square root of 3, and of course there's a negative there, but divided by 2. So that would be 2 square roots of 3. This goes into this once, goes in here twice, giving you 2 times square root of 3 with that negative out there. Okay, so when I try to put this in rectangular form, this is the rectangular form of a complex number. So this is equal to x is first, and then it's plus the b value times I. The b value is the same thing as y. So let's see, since it's negative, a plus followed by a negative would be negative 2 square roots of 3. And that y value, or what we call the b value, is the coefficient to the I term. And there you have the polar number that they presented you with originally, r times cosine of theta plus I times sine of theta, now written back in rectangular form. Okay. Okay, moving on to example 9. In example 9, same thing. Okay, you're wanting to find, this is in polar form, so you have r and you have theta. You want to get this complex number in this form because it's the same thing as it being written like this. Okay, it's just that, you know, in the formulas that we've learned, we have formulas that state x is equal to r cosine theta. So why don't we rotate to the theta that they've given us here. And I'm just going to put the diagram right here. If you go to 3 pi over 2, this is 1 pi over 2. This is 2 pi over 2. This is 3 pi over 2. So if you rotate all the way to 3 pi over 2 and you're on a unit circle, then you're at this point right on the negative y-axis, and that has the coordinates 0, negative 1. So whenever you land right on an axis like that, you can't draw a triangle. You have to know that the x-coordinate is the cosine and the y-coordinate is the sine. So finishing this, it would be the r value, which is present right there. It's the 7. And then the cosine would just be 0, which is 0. So I have my x value, and now I would like to get my y value. So y is equal to r sine theta. That r value, once again, is 7, and the sine value at 3 pi over 2 is negative 1. So negative 7. And then I can take it right back here and write this polar complex number as a rectangular complex number. Okay, so the x was 0, and then the y value, so it would be plus y times I, but the y is negative. Okay, 0 take away 7i is the same thing as just negative 7i, so you can give that. Sometimes the imaginary portion is 0, as it was in this case. Okay, moving on to example 10. Okay, this one says write the complex number in rectangular form one more time. And so we're looking for x, r cosine theta. Okay, now 7 pi over 10, you have to do a calculator answer, because that is not a special right triangle. So it's the r value, which is 0.2 times cosine of the theta that you're seeing right here, which is 7 pi over 10. You need to be in radian form for this because you're feeding in a radian type answer. Okay, so as we feed this in, mode needs to be in radians, which I believe we are still in. And check that real quick. Mode. Yep, mode is in radians, so quit out of there. Let's clear that out. We're going to go 0.2, our r value, times cosine of 7 pi divided by 10. And we get negative 0.117. Hold on 1 second. Let's write this right here. So this will be, let's see, use integers or decimals for any numbers. Do not round until the final answer, then round to the thousandths place as needed. So that would be thousandths place is right here, the 7, so negative 0.118. Negative 0.118. Okay, so we have that value for x, and then the y coefficient is going to be r times sine of theta. And then this will be 0.2 times the sine of 7 pi over 10. Number 11. Okay, so putting that into the calculator, this would be 0.2 times sine, and this is going to be 7 pi divided by 10. Okay, and this would be to the thousandths place, 0.162. Okay, and then we're going to write that in rectangular form. Okay, so that rectangular form once again is x plus y times I. Same thing as a plus b times I. So negative 0.118. You can put the leading 0 if you'd like. I believe you'll be marked wrong in the homework if you don't put that 0. It's up to you. So there's the x, and then it'll be plus y times I. There's the y, and that is the coefficient of your I term. Okay, so that's that one. Then moving on to this one in number 11, it says write the complex number in rectangular form, and you can see what the r is, you can see what the theta is, even though it's written in exponential form, which is kind of a, shortened version notation, but you still have the values that you need in order to go into rectangular form. So again, this is something that has nothing to do with special right triangles. So you don't need to spin there or draw it. You can do that by your calculator, and that's why you see them saying round it to 3 decimal places, because they know it has to be done by the calculator. So x is equal to the r value, which is 7 right there, times cosine of theta, so just 7 times cosine of pi over 10. We'll put that in our calculator. This is okay, so 7 times cosine, and then it's pi divided by 10, and then that's 6.657. So we have that x value, and then the y value would be r times sine of theta. And that would be 7 times sine of pi over 10. Go to your calculator once again. 7 times sine of pi divided by 10. And then here you get 2.163. And that'll be the coefficient of your I term. Okay, so again, when they say rectangular form, regardless of the way they deliver the information to you, you're looking for R. You're looking for x and y using the r and theta that they've given to you. And they may give you the r and theta in exponential form, or they may give it to you like this in full-blown polar form, where the r is out front and then you have the form cosine theta, I sine theta. Okay, so in rectangular form, which is just x plus yi, it would be 6.657 for the x value, and then the y is 2.163, and that's the coefficient of your imaginary term. Okay, that completes number 11. Okay, then we come to finding products and quotients. So here are the definitions for finding products and quotients. Right here we have how to find a product. Has to be in polar form. So when you're finding the product of two polar numbers, all you're going to do is multiply the r values. That's what you see out here, r1 times r2. And then as far as the thetas in the first polar number and the thetas in the second polar number, that's why they're calling them theta 1s and theta 2s. These are the thetas for the first polar number. These are the thetas for the second polar complex number. So you multiply the r's out front, and then inside here for your cosine term, because you're still going to be delivering a product that's in polar form, polar complex form, where you have a real portion expressed as the cosine term and an imaginary portion expressed as the sine term. So for the cosine term as well as the sine term in your product, you just add up the angles from the first polar number and the second polar number. And whatever you get here, of course, you're going to get the same thing here. This can be written in a shorthand version form, the Cis form, where you would just give that the product of those r values out front, and instead of writing cosine plus I sine, just instead of that, cis, and that new angle that you got when you added. So just you have to see what they want in the instructions. There is also a formula for finding a quotient of two complex numbers. So here's one complex number, here's another complex number, both in polar form. And if you're going to find a quotient, you take the first R value divided by the second R value in that order, numerator, denominator. And then instead of adding the thetas like we did when we were finding a product, you're going to subtract them. And again, in order. The thetas that were part of the first complex number, it's going to be that theta first minus the theta from the second polar number. And that will be your product. You'll have one angle here after you do the subtraction. And you'll have one value here. It may be a fraction, it may be a decimal, it may be an integer. If you want to give it in the shorthand version, you could take this quotient and represent it like this. Whatever you got for the quotient of the R values will go out here. Instead of cosine I plus I times sine. Excuse me. This cis will replace cosine plus I times sine. And the one angle that you got when you subtracted will go right in there. So I'm going to demonstrate that, how to find product, how to find quotient. Okay, so here is example 12. And you have one polar number, you have another polar number. And you're being asked to find the product as well as the quotient. Just give me a minute. Okay. Okay, so when you're finding the product, the formula goes like this. You're going to multiply, okay, this will be to find Z times W. You're going to multiply the R value, so 2 times 4. And then inside here where you'll put the polar version of this complex product, it's cosine. And you're going to add the two angles together. The 2 pi over 9 from the first polar number added to the angle from the second polar complex number. And then here's your imaginary portion of your product, always related to the sine and that same angle, that same sum. Okay, so this product will be 8 times cosine of 3/9. 2 over 9 plus 1 over 9 is 3/9. And if you got 3/9 here, you're getting 3/9 here. You're going to want to reduce those and give them in their most reduced form. So 8 times cosine of pi over 3 plus I times sine of pi over 3. And let me check and see how far they want you to go here. Yep, that's it. All right, so that's as far as, because you can go further if you actually go and get the values of pi over 3, but they want you to stop there. So it says the product is, so all of this would go right in here. And then if you're going to give the exponential form of this answer, Remember, when you're giving something in exponential form, it's given like this. So the R value would be the R you got after you found the product. So it would be 8, and then it's E times I times theta, and this new theta that you got in the product is what you're looking for theta. So pi over 3 times I for that exponent on E. Okay, then if you're going to look for the quotient of these two complex polar form numbers would be use the R value from the first polar complex number, which is 2, divided by the R value from the second polar complex number. And then in his side where you're given cosine of theta plus I times sine of theta, subtraction happens in there. So it's the first theta in this order minus the second theta. And then for the imaginary term, it's the first theta minus the second theta. Same thing here and here. Okay, so this will be 1/2. Cosine term will be 2/9 minus 1/9, or just 1/9. 2/9 minus 1/9. And if that's what you're getting on your cosine term, then you're also getting that on your sine term. I actually need a parenthesis, I guess. Okay, so this will just be pi over 9. Okay, and that is the product in straight polar form. If you're asked, so all of this would go right in here. And then if you're asked to give this in exponential form, same thing, use this formula right here. That R value that we got in the quotient was 1/2. Then it's E raised up to a power of I times theta. And the theta they're talking about is this new theta that was formed when you did the subtraction for the quotient. So it would be pi over 9. That's the theta, and you can put the I in front and back. Okay, so that's both the product and the quotient in polar form as well as in exponential form for both. Okay, moving to number 13. Example number 13. Okay, I'll do some of the work here. We're going to be doing the product. So we're multiplying this R times this R, getting 81. Then it's cosine. And when we're doing a product, we're always adding the angles. We're adding the theta from the first polar complex number to the theta from the second polar complex number in both the cosine term and the imaginary sine term. You can get your calculator to help with those different denominators. Okay, so when you put this in your calculator, you would just put 1/7 plus 1/8. And instead of hitting enter, you hit math enter, enter. The calculator will get a common denominator for you and reduce it. And then you can put the pi back on, but you don't need to enter the pi in your calculator. Just enter 1/7 plus 1/8. Just to get a little help with getting common denominators. So 1/7 plus 1/8, and instead of enter, hit math, enter, enter. And it gives you common denominators on those fractions and reduces it. So this is 1556 with a pi on there. And then for your imaginary term, same thing. You've already done the work for adding 1/7 and 1/8 pi, and it came out to be 15 over 56 pi's. Okay, so all of that is the product for this one. If you're going to put it in exponential form, let me just check that real quick. If you're going to put it in exponential form, just follow that same formula that we've been using in order to put it in exponential form. Okay, so that is R equaling R times E raised up to a power of I times theta for exponential form. And so the new R value that we got when we did our product was 81. And then it's E raised up to a power of I times theta, and the theta was 15 pi over 56. And that's part of an I term. That exponent is part I, part theta. Okay, if you're doing the quotient, I'm going to do the quotient down here. Then it goes the first R divided by the second R, and then we do our cosine sine terms, but this time we're subtracting. We're taking the first angle and subtracting the second angle. Same thing on your imaginary term. So once you get it for here, you can just copy it here again. So this will be equal to 1. Get your calculator to help out here. You can get your calculator to do 1/7 minus 1/8, and then you can just paste the pi back on there after you get that from your calculator. So 1 divided by 7 minus 1 divided by 8, and hit math, enter, enter. And you get 1 over 56 pi. Put that pi back on there. So you can just put pi over 56. Okay, and that is your quotient. So all of this is this answer right here. And then for exponential form, same thing, follow this. The R value that you got was 1, and then it's times E, so you don't have to write the 1. You can just write E raised up to a coefficient of I times theta. And that new theta was pi over 56. Pi over 56, don't forget to put the I. And you can write it without the 1. Okay, last problem, finally, is another product in quotient. I think there's some negatives going on here though, so maybe a little bit more complicated, not much. Okay, so here we go. We're going to find the product. So it's Z times W. And when we do Z times W, let's see what this is. Write each one in polar and exponential form. Okay, so here's the problem with this. Notice that these formulas that they gave you, you need to have the numbers in polar form, but yet look what they're giving you. These are in rectangular form. And those formulas for getting these complex numbers multiplied out, they only work if you have numbers that are in polar form. So this is actually a double problem. Not only do you have to use the new formulas that we just learned for finding products and quotients, but you're also going to have to put this in polar form. So why don't we do, we're going to have to use the space as best we can here. Let's first get these in polar form. Okay, so for this one, when that goes, z is equal to 10 plus 10i. If we want to put this in polar form, we need an r value. R is equal to x squared plus y squared. This is x. This is y, that other 10. So you have 100 plus 100, 200, or in other words, 2 times 100. You can take the square root of the 100. It comes out as a 10, as the actual square root of 100. That's done with, and the 2 remains underneath. There's your R value for that first rectangular complex number. Then you also need the theta. This is in quad 1, 10 plus 10i. So our reference angle will be the same as our actual theta. So whatever we find as the theta right now, that is the final theta. So tan of theta is y, that's that, over x. And if you don't know what the theta is that goes with a tan value of 1, you could always do this. You could always go inverse tan of 1. And, you know, I say that if you're going to be looking for angles, that you should have the mode in degrees. So you would just go mode. You would take this to degrees, press enter, quit out of there, and then you could go inverse tan of 1. If you can't remember what it is, you find out that it's 45 degrees, which is the same thing as pi over 4. So you know the theta, you know the R value. So this complex number right here that's in rectangular form, in polar form, it is R times cosine of theta. Because if you're going to find the product in the quotient, it has to be in this form, plus I times sine of pi over 4. Okay, we now have the z in complex form. Now we have to go through this again in order to deal with w. W needs to be in complex form. So let's see, for w, and maybe I'll do the product and the quotient down below. Let's see if I, so this is for z. I'll keep everything straight here because it's going to be a nightmare. Now we're doing it for w. W is square root of 3 minus I. So when you're going to find the R, it is x squared plus y squared, and that's a negative 1. Okay, so this R value, this squared is 3. This squared is 1. You end up with R is equal to square root of 4, which is equal to 2. So now you have your R value on this other rectangular complex number. Then for the theta, we can go, now let's see, what quadrant are we in if we're at square root of 3 minus I? We might need a little picture there. So let's see. For tan of, now this one's not in quad 1. When you're at positive square root of 3 but down negative 1, that's in quad 4. And remember, this a and b value is also like an x and a y. So if you're at positive x, negative y, you're in quad 4. We need a theta that's in quad 4. And our calculator may give us to that, may give us something like that. So let's see, we can go like this. We're going to go that this is equal to y over x. So this is equal to the y value is -1, and the x value is this. And if you want to get the angle out of that, you go inverse of -1 over square root of 3. Just go inverse of this, and that'll be equal to either a reference angle or maybe an angle that's actually given right in quadrant 4. Let's see what we get. Okay, we're still in degrees, so we're going to go second inverse tan. We're going to put in -1 divided by second function square root of 3. Close that up. Close that up. -30. That's actually in quadrant 4. -30 is the same thing as pi over 6. So you don't need to worry about rotating the other way, because as long as you have an angle that's in quad 4, you can use this for purposes of getting the product and the quotient. So we have another theta, we have another r. So this particular number was r. Putting this in polar form, cosine of the angle that we got, which is -pi over 6. And then the imaginary portion, which is always related to sine, would also have that same angle. Okay, now these are certainly not the final answers. It's just that you cannot use these formulas for finding product and quotient unless they're in polar form, and that's why this problem is so much work. But I do now have them both in polar form. I found the r and the theta for 10 plus 10i. I found an r and a theta for square root of 3 minus I. So I have two polar type numbers, and now I can jump into the product and the quotient. So the product goes that you are multiplying one r times the other r. And then you're adding the thetas. So the theta would be, for the first polar number, pi over 4 plus the other one is -pi over 6. So that's the same thing as just pi over 4 minus pi over 6. For your imaginary portion, you'd have the same thing. Pi over 4 minus pi over 6. Okay, cleaning this up, this would be 2 times 10, 20. Square root of 2. We'll get our calculator to help out with this. We'll go 1/4 minus, because a plus followed by a minus is just a minus. We'll go 1/4 minus 1/6. So 1 divided by 4 minus 1 divided by 6. And instead of enter, hit math, enter, enter, so that it gets common denominators and reduces it. Okay, so 1/4 minus 1/6 is pi over 12, but paste that pi back on there. Okay, there's 1/12 of a pi. Whoops, I forgot to write cosine. Okay, so that's the angle. That 1 pi over 12 is the angle for cosine as well as sine, as well as the imaginary sine term. Okay, and if you're going to give this particular answer, This is one of your answers. I'm not going to try and cram it in that space up there, but that's the product for z times w. If you're going to give this in exponential form, then you're just using that same formula, putting it in this form, r times e raised up to a power of I times theta. So that r value would be the r value that you got after you did the product. And then e raised up to I times theta. The theta would be this new pi over 12 that you got after you did the product. So pi over 12 times I. Okay, and there it is in exponential form. Okay, then we're going to do the quotient. So the quotient here would be the first r value, which was 10 square roots of 2. It matters which order you do it in here. When you're doing the quotient, it has to be the first r value divided by the second r value. And then it also matters the order that you are subtracting in. So for cosine term, it's going to be the first theta, which was pi over 4. We're doing a quotient, so we're subtracting. And that second theta was negative pi over 6. So we got a double negative there. And then for your imaginary term, it would be the same thing. If you want to write it in its cleaned up form, it would be pi over 4. This combined with this would be a plus, so it's really pi over 4 plus pi over 6 after you apply that double negative. Okay, get your calculator to help out. Just put in 1/4 plus 1/6, and then we'll paste the pi on in a minute. So 1/4, 1 divided by 4, plus 1 divided by 6. 1/4 plus 1/6, hit math, enter, enter, and you get 5/12. Let's clean this up a bit. This would be 5 square roots of 2. And we got our calculator to figure out that 1/4 plus 1/6 was 5/12 of a pi. And that's your quotient. And if you're going to give that answer in exponential form, okay, then it would just be the quotient, but we'd be using that form r times e raised up to a power of I times theta. So that r value would be this right here, what you got when you got the quotient, and the theta would be this. So 5 square roots of 2, and then it's e raised up to a power of I times theta. So that new theta is 5/12 of a pi times I. Okay, and that completes section 9.3.